in this sequence, we will discover what are called references in OCaml, which are similar to variables in other programming languages. Well, what are variables in typical imperative programming languages? Let's consider this little fragment of program that could be part of a C or a Java program. The first line is a definition of a variable I. I is the name of the variable. It is initialized to 0. But this name I may refer to a memory cell when it is put on the left of the equal sign, this memory cell that you write in, or to the content of the memory cell, typically when it is on the right of the equal sign. But things can become pretty complicated, and in general you can make knots in your head, think about L values, R values in different programming languages. But if you really want to have variables in OCaml, we can use the mutable records we have just discovered to get the same effect. So again, let's consider this program, and an integer variable I initializes to 0, and then later on somebody decided to increment this value by adding 1 to it. Well, this can be written in OCaml by defining a record type, we will call it reference cell, ref cell, that has just one field, which is called the content of type integer, and we define this field as mutable. Now the first line of the imperative program we have there, int I equal to 0, can be actually written as let id, the name of a record which is initialized with the content field equal to 0. And then the modification can be done in place in the second line. You see here we are saying we are updating the content field of I with the old value of this content field plus 1. And here this update operator clearly indicates what is read and what is written. When you OCaml, actually you have a predefined ref type that is defined exactly this way, but has a special syntax to be used in a more concise way. Actually, this is called a reference type, as well as instances, we all call them references. The definition is exactly like this. We define a polymorphic record type with a mutable single field, name and contents that contain the information you want to store. This comes with really convenient syntactic support. You have a function predefined for you, which is also called ref, that is able to create a reference. We pass the function the value to store in the reference. It provides us with a reference initialized to this particular value. Now you have a prefix operator, bang, here, which is used to explicitly indicate you want to read the content of the reference. And then you have an infix operator, colon equal, which is used to perform update of the content of the reference. So this will mean update the content of the reference R by putting in there the value V. Let's see this at work on a simple example. Right, so now let's get familiar with references. We start with a very simple example. Here, on the first line, we are defining an identifier I, which is a name for a reference that contains a 0. So you remember this ref function here takes a value, creates a cell that contains exactly that value. So we pass it to the interpreter, and you see now what the compiler tells us, that it has seen the definition identifier I. That is the name of a reference cell containing an integer, and the contents is really this 0 here inside. Well, again, if now I try to look at what is I get the same result. It is always this reference set with content 0. Now let's start to modify the reference. We have seen that to modify a reference, to make an update, we have this colon equal operator that changes the content of the reference cell on the left by the value which is on the right of the colon equal sign. And what is the value we are taking here? We are adding 1 to the content of the I reference cell. And the content is taken by this bang operator here. So we would expect to see now I change in value moving to 1. Well, the system tells us that this operation has been performed as it is only working by side effects, the result is of unit type. Now if we look at I again, well, now the content of the reference cell has been changed and contains 1 as expected. So basically this is a way of simulating variables, but the difference is now for us it is really clear when we are taking the content of the variable, you see we are taking this content operator with bang, and when we are updating the content of a variable by this update operator colon equal. Okay, so let's see an example. Imagine we want to compute the integer base 2 logarithm of an integer n. Well, a very easy way of doing this is just counting how many times you can divide this integer by 2 before getting below 1. Okay, so let's program it the same way you would do it in another programming language, in an imperative programming language. We define the log2in function. It takes an integer n as a parameter. Then we define 2 variables. Well, now we know the real name here is references. One named count, which is a reference initialized to 0, and another named v, which is initialized to the value n, which has been passed as a parameter. Then what we do a simple while loop that keeps dividing the original integer by 2 until it goes below or equal to 1. And at the same time increments this counter to keep track of how many times we did this operation. At the end of the loop, we write on the content of this counter count. So you can pass the definition to the compiler. You see the compiler tells you it is just a function that takes an integer and return integers, and as you can expect, the base 2 logarithm of 16 is really 4. 1024 is 10, and of 1 million it is 19. Well, okay, so let's try now something a little more sophisticated. Let's try to read a list of integers from the standard input. Well, we can start by defining a function that reads an integer. It's pretty easy. We just use a readline function we already know. This will return a string, and then we convert it into an integer. By the way, this is a function which is predefined in OCaml and is defined exactly this way. Then, to write a readInt list function, what we can do, doing it really in an imperative way, we use a variable, our reference, which is initialized to the empty list, and this variable will be updated in a loop here, which is defined in a new function we will call doRead. This is an infinite loop, while true do then, it will never stop. And in this loop, we read an integer, we add it in front of the content of the our L variable, and update the content of our L variable. So you see here again, we are taking the content of the value of L to the concatenation with the integer we have just read, and then use this value to update the content of L, so we have a new value coming out. Well, when will this loop stop? As soon as we get an exceptional condition. This can happen if you type something which is not an integer, so readInt will raise an exception, or, for example, if you finish the standard input. As soon as we get an exception, we want to catch it, so this is why we have a try with around this infinite loop, and when the exception arrives, the computation is stopped and we just return unit. Now that we have these two elements, I mean our reference and the infinite loop, we can just write doRead. This will read until we stop the computation with an exception, and as soon as we have done this, we will find inside our variable L all the integers we have typed in, but they are in the reverse order. So to put them in the right order, we just call the listRef function on top of this. Fine, so let's see if this really works as expected. Well, fine. So our compiler is happy. They type check properly, and we have defined a function that waits for a unit element and returns the integers list read on the standard input. So let's try it out. Okay. And you see, now this readInt has been called for the first time. We have a pop-up in our environment, which is used to read the line. I will enter the integer 1. Then it keeps coming up again. So let's type 2, 3, 4, 5. Now I want to stop this, so I enter something which is not an integer. And here it is. We get our integer list in the proper order. So to sum up, the usual variables of imperative programming languages can be implemented via mutable records. This is exactly what can be done in OCaml. The notion of memory cell and of contents of memory cell in this interpretation of mutable records are really distinguished, and we have a special syntax which is available for writing more concise programs using references. And so after having seen all these notions in this week, we have concluded our short exploration of the imperative features of the OCaml language. So if you really want, you can write full imperative programs in the language. But our recommendation is to use these features only where they are really, really needed for efficiency reasons.